Good morning, everybody. Hope you're doing good. I hope you're safe at home. My name is Quentin Ledebeur. I am a product definition engineer at Wurth Elektronik. And today I am with Hebali Ahatna from Analog Device, who's a product marketing manager. And together we conducted some EMI testing at ADI to give you guys some practical DC-DC EMI improvement techniques for your design. So now I'll pass on to Hebali, who will start the presentation talking about the board we're testing and the different results we are looking for.
Welcome, everybody, and welcome, Quentin. Thank you for the introduction. So real quick, let me start by saying that today we're going to talk about some EMI improvement techniques around magnetics, around the inductor that you may use for power supplies on your board. So we're going to use some actual demo boards which have been tested in the EMI chamber that we have here at Analog. And we're going to provide you with some tips that I think will be helpful for you to learn how to utilize your magnetics in a more EMI advantageous way. So today we're going to be talking primarily about boost type converters or buck boost. So just a quick reminder of the simplified topology of a boost converter. Here you see it, inductor, diode, and switch with a load and a supply. And I just want to remind you that, of course, a MOSFET in a switch mode power supply contributes high voltage ringing, which propagates across traces and components and causes EMI issues. In addition to having issues with the MOSFET creating noise, having an inductor near the MOSFET, as is usually the case, will create some coupling between the switch and the inductor. Typically, it's interesting to analyze the proximity, the layout, the orientation of the switch and the inductor, and their interaction between the two. Distance can play a significant role. The geometry, meaning the dimensions of the trace that connects them, the orientation of the inductor, and how the inductor is constructed can play a significant role in how EMI is propagated through the board and how it manifests on your results when you test. Today, we're going to cover three particular topics that should be of interest to all of you. First, we're going to talk about changing the layout, perhaps depending on how the noise is coupling on your board, how to change the inductor depending on the geometry of the inductor itself, and perhaps in some cases, the most advantageous case is how we shield the inductor. All right, so our first topic of today is going to be changing the layout. So we're going to talk about, in particular, or changing the layout to improve inductor immunity or compatibility, depending on the case. But essentially, we're going to focus on a few layout techniques regarding the inductor on the board. So first, a few reminders and tips that are quite useful, always good to know. As we know, antennas resonate depending on the wavelength of the signal, of the incoming signal. And so it's important to take note whenever we design a PCB board, when we lay out the PCB board, that an even multiple of the frequency in question can excite a trace on a board. The trace can pick up this noise or this signal and propagate it through it. Another situation could be the trace may not propagate it as a conducted signal, but it may actually just radiate it out. So if it's the right dimensions, it will play the role of a parasitic antenna. So for instance, if we have a signal at 500 kilohertz and the wavelength of a trace on the board matches that 500 kilohertz signal, then that trace will be a parasitic antenna, which will radiate noise throughout the board and into space. So we may have a combination of radiated and conducted noise. I would like to mention that it's important to take note of the direction of the magnetic field on from an inductor and how it couples through a PCB. So we have different components on a board. These components, depending on the direction of the magnetic field, may couple directly and heavily with the inductor. So we have components such as traces on the board, laying down horizontally on the board in different directions. And we also have vias which go right through the board vertically. So depending on the orientation of the magnetic field of our inductor, so we're going to talk about the construction of the inductor in a few more slides. Quentin will give you some very interesting information about how inductors are constructed and why some inductors tend to couple more than others, whether they be shielded or unshielded. And in addition to that, it's important to note that anything that, whether it be vertical or horizontal, sitting on the board, if it's metallic, most likely, and ferromagnetic, most likely will couple with the inductor. So legs from a capacitor could be also an issue. Other shielding material around the inductor, or rather components that are being shielded and are in proximity with the inductor, could also couple. So anything on the board that has the right orientation in relation to the magnetic field of the inductor could couple and create noise, whether it be radiated noise or conducted noise. In other words, the traces could pick it up, the noise from the inductor or from even the MOSFET. The MOSFET also, the voltage ringing creates a magnetic field too, which depending on its orientation could also couple. So this noise either propagates through the air or through components on the PCB board. So to make this more interesting for you guys, we will give you some tips on the next slide, but just to drive the point through to completion, I'd like to say that the best way to avoid any kind of coupling is to move components away if your board permits it. Sometimes it's not necessarily, may not be necessary just to add more distance, but just to reorient components on a board to make them couple a lot less. So take a note that if you can shift the direction of your traces, move away planes, power planes or ground planes, and perhaps also move around vias, we can minimize the coupling that occurs between the MOSFET and the inductor and different components on the board, or the MOSFET and components on the board. So distance can be your friend if you can reorient your components appropriately. So our first example that we have here today, it's buck boost Type C, USB PD Type C automotive charger. And here we see some pictures of the board. And first, let me point out what you see on those two yellow boxes. You see an inductor. This is a power inductor for this device, for this USB PD Type C buck boost. And take a look at the letters on top of the inductor. You can see they are not oriented the same. They have been rotated. And so what we're seeing here is essentially the same inductor, exactly the same inductor, but it has been soldered on the board in two different orientations. Why have we done this? Take a look on the left. You will see the two orientations. And so what we're trying to show here is two different orientations where we point the start of winding of this inductor either to point towards the buck switching side or towards the boost switching side. And if that is not readily clear, take a look at the simplified schematic that we have here. And you can see that we have a 4-switch buck boost. This is the topology we're using for this device. And we have the inductor sandwich between the two MOSFETs that generate the buck mode and the two other switches that generate the boost mode. And so depending on how we point the start winding of your inductor, we can have a different effect from the point of view of EMI. So we are going to discuss that in the next few slides. So please continue with us. We're going to move on to showing you specific results from changing the orientation of the inductor. So a little bit more about this specific design, just so that you are more familiarized with what we're looking at. On the right, you can see again the buck and boost sides of the inductor and of the system as a whole. You can see two colors. We're using two colors here. We're using red and blue. The red one, we're gonna refer to it from here on throughout the rest of the presentation until the end as orientation 1, and we're gonna define it as the start winding facing towards the buck switching node. And the blue one, orientation 2, it's defined here as the start winding towards the boost switching side. And more about the actual buck boost that we're using here is a 350 kilohertz switching frequency device. And also it has a spread spectrum frequency modulation, meaning that we spread the switching frequency over a small bandwidth to reduce the overall noise. It has been tested to pass CISPR 25, in other words, the automotive standard, using an inductor L1 in this case, which is 6.8 microhenry. In addition to that, we've done two types of tests. According to CISPR 25, we've done the radiated and conducted emissions, both peak and average. So hopefully with this information, you can get a good picture of what happens to the inductor when you change its orientation on the board. So here are the first results that we have available. We are looking at average radiated emissions. We have in red, again, orientation 1, and in blue, orientation 2. And we have two modes of operation. We have a 27-watt output buck mode, we call it, and then we have a 60-watt boost mode. So in other words, we are at 20 volts, 3 amps for the boost mode, 60 watts, and for the buck, we are at 9 volts, 3 amps. Same number of amps. The only thing that changes here is the voltage. Input voltage doesn't change. We have the same for both, 14 volts. And here we can analyze both plots that we have here, both graphs. We on the left side, we have buck mode, and we have, as I mentioned, orientation 1 and 2. Take a look. So the red one, as I mentioned, points towards the buck switching side, and the blue one points towards the boost switching side. So in this case, you can see that pointing our inductor, the start winding, pointing the start winding towards the boost mode, while we are switching power supply is in buck mode, generates quite a bit of noise. So take a look here at this blue waveform here. This is our boost pointing start winding in our buck mode, and you can see we are barely passing here. However, as soon as we switch turn around our inductor to face the buck switching side, then this noise goes down significantly. We see significant improvements, and you can see how this is the case throughout a wide frequency bandwidth from kilohertz into the megahertz range. Once we get higher than that, depending on whether you're doing average or peak, and as you may know if you've done enough EMI testing, the difference between the red and blue lines here is so small that potentially you don't have much difference. So perhaps in the high frequency bandwidth, we're not seeing a significant change, but on the lower frequency bandwidth, we can see a significant improvement. Now let's take a look here at the plot on the right. We can see exactly the opposite. Now we are in boost mode, and if we take a look at what happens when we have our inductor pointing towards the buck switching node, then we are not passing. Before we were barely passing, now we're not passing. And the noise is quite significant throughout the entire range. In this case, we're seeing coupling, potentially heavy coupling between the inductor and the board, some components on the board, like the MOSFET. But when we change to orientation 2, in which we point the inductor toward the boost switching node, take a look, then we can see some immediate benefit. There is some noise reduction. It's quite significant throughout, again, a very similar range to what we saw before. Once we get very high up in frequency, it could change depending on the particular date that we test. But here, this is definitely very relevant. So that's the first result that I want to show you. We're going to summarize what this means in the next few slides, but let me show you a few more. So let's continue. Now, we are going to look at conducted emissions. We're going to use a current probe, and we're going to probe the output. And so, again, we have orientation 1, orientation 2. Again, reminding you that all these tests are, we are doing CISPR 25 limits, class 5. And again, we have our two modes of operation. We have, for our switching power supply, we have the buck, the boost. And again, we have the same thing. All we are doing is changing the inductor from one orientation to the other orientation. And here we see a similar trend. If we are in the buck mode of operation, if we face our inductor towards the boost switching node, we are failing. However, if we point our start winding of our inductor towards the buck switching node in buck mode, then our situation again improves. In this case, we are doing conducted emissions. You can see how there is a significant difference, enough dBs that I would call that more than enough margin. In some cases, perhaps there are some peaks that don't look that great, but nonetheless, overall, this looks much better. Now, if we look to the graph on the right, we see a similar situation. Now we are in boost mode. Now we are pointing our inductor in two different directions again. If we point towards the buck side, switching node, you can see we are failing, but if we point it towards the boost side, we are doing much better, especially in the low frequency bandwidth. All right, let's do one more. Now we're going to do current conducted emissions with a current probe, and we are going to probe the input, and we can now take a look at the same two situations, buck and boost mode, and two orientations. Again, similar stories, a little bit different. Let me point out some of the similarities and differences. Here we don't see much change on the low frequency bandwidth, but on the high frequency bandwidth, we can see a significant change when we turn our inductor from one orientation to the other one. When this is in the buck mode, and then on the boost mode of operation, we have again two orientations, and you can see how if we point in this case towards the buck switching node, how on the low frequency, on the very low frequency, we're getting some improvements, and that turns around actually as we move in onto the high frequency bandwidth. Then the buck oriented inductor fails, but if we point our inductor then in the boost configuration, then we get some significant improvements. In either case, we're passing. So in this case, it looks like it's more beneficial just to have the inductor pointing towards the boost switching node. So those are some of the results that we saw. We're going to talk about what this means and how potentially you can interpret this to choose the best inductor in the next few slides, and probably Quentin will give you some information about that. But let's continue forward.
Okay, so thank you heavily for presenting all of the results. Now for the analysis, I think that's pretty clear that the inductor orientation actually makes a very significant impact on the emissions, whether it's conducted or emitted. You can see a clear impact. The best emissions in boost operation mode are of course obtained when you put the start of winding towards boost switching node, and the best emissions in buck operation are of course obtained when you put the start of winding of the inductor towards the buck switch node. Now, for this specific application, we have a buck boost, so you still need to pick one of them. For this specific case, what we would normally do would be to actually pick the best conducted emission results, because we know that by experience, it's a little bit harder to kill conducting noise versus radiating noise. Not that it's actually more complicated, but also because we have a solution for the radiating noise where we don't necessarily have one right away for the conducted. So for this specific case, what we would choose would be to have the inductor starter winding oriented towards the boost switch node. So that's what we have decided for this specific design. Now, we've seen how the starter winding affects the EMI performance of the board. And what I would like to go through with you is also a few other properties of the inductor that will affect the EMI performance. We'll of course go through the starter winding and explain why the starter winding is so important and how does it translate in terms of inductor construction. So the first thing to look at is what kind of inductor we use, what kind of inductor we deal with, and how are they performing EMI-wise. So I've put on this page three types of inductor. Both of them are ferrite, the two left ones, and one of them is iron powder on the right. Now, when you look at ferrite inductor, you typically have either standard sizes like the middle one, or specific sizes like the left one, which are maybe fully shielded. But whatever package you're looking at, you'll always have some kind of legs or pads coming out of the parts, or you'll have some sort of openings in the ferrite. And those are all of the weak points that the EMI and the magnetic flux will use to actually leak out of the inductor. So regardless of the design you pick and how well shielded is the ferrite part, you usually always have a weak point where your flux is actually coming out of the part. Whereas on the other side, when you look at the power inductor side, the iron part of inductor, you can actually see that the molded technology on this part, the fact that we can overmold the winding into the parts actually makes it fully shielded. On top of that, you can see that we can actually pack the pad underneath the parts, which provide extra shielding as well. So you don't have the pad coming out on the side of the part and therefore exposing open winding. So that's kind of the first thing that you can look at. Now moving on into the start of winding, why is this so important and why does it have so much effect on the EMI performance? Now I'll distinguish two cases, of course, the multiple layer inductor and the single layer inductor. So for multiple layer inductor, follow me here. We're going to start winding at the bottom left of the part, wind our way up to the top, and then wind our way down and finish at the bottom right. Now, if you orientate the winding towards the switch node, you will have your noise being actually effectively shielded by the second layer itself of the parts. So you will actually avoid and prevent this noise to be leaking out because you have an extra shielding around this first layer of winding. Now, if you do the opposite, you have that now the second layer that's directly on the outside of your part, which is much closer to the edge of your core material, and so which is more likely to leak out. So that's for the multiple layer inductor. That's why the start of winding is important. Now you'll tell me, of course, not all of the parts are multiple layers. So how does it work for single layer parts? Well, you can see here why. The same thing. You start with the bottom left corner of the part. You wind all your way up. But at some point, when you reach the top of the part, you still have to come down. And when you go down from the top winding to the bottom right side, you actually create a straight piece of wire, which basically acts like an antenna. So again, if you orientate this antenna, so the end of the winding towards the switch node, you will expose yourself. You're more likely to have your noise be directly emitted as a radiating noise. And the same thing for the starter winding. If you put the starter winding towards the switch node, when you start directly into the winding, and you're less likely to have emissions coming out of this inductor. So that's basically the explanation of why the starter winding is important and why it should always be orientated towards the switch node. Another important construction tips is to look at how the inductor is actually winded. Is it winded vertically or is it winded horizontally or something else, which maybe does not exist. But so far, most of them are either vertical or horizontal. And what it will change actually is the way the flux is actually moving into the ports and the way it's actually moving also outside of the port, of course, and the way it will cross the PCB coming in and out of the PCB. So you can see like for vertical winding, your magnetic flux is actually coming down on the outside of the part. So it kind of creates a square of, actually, if you can see on my bottom schematics here, you can see the crosses is magnetically going in the board, and the dots is a magnetic field coming towards you, so outside of the board. So you can see that the flux is moving way differently if you look at the vertical winding versus horizontal winding. You will be able to shield vertical winding inductor effectively with bias, when for horizontal winding, you will be able to do it, but you can see, of course, that at some point underneath the part, you'll have some horizontal flux, which is going to be very hard to shield with bias. So you might consider other options, maybe ground shielding, maybe something else, but you need to be aware of that and place the inductor on the traces consequently and just plan ahead for that. So that's for the inductor construction, and that's why it's also important to know what inductor you use, what winding it has, and where's the start of winding. Now, as we said, we have a solution as well for the radiating noise of the board. And now I'll move on back to, I will give the mic back to Heberly so that he can tell us more about shielding the noise source and the different shielding solutions that you can have to mitigate all the radiating noise on your board.
Now we're going to be talking about shielding the noise source. Another way you can reduce noise. This is perhaps the brute force method, but nonetheless very effective. So we're going to talk about some benefits and some drawbacks of shielding your board. There are different ways to shield a board. These days, all could be done in production if necessary. I guess in the EMI chamber, you're all familiar using your standard copper tape. But once you go into production, you want to replace that with a nice, neatly made shielding box or shielding can. And we're going to talk about some different kinds of constructions for shielding cans in just a little bit. But there are also ferrite materials, which are very effective in the high frequency ranges, anywhere between hundreds of kilohertz to tens of megahertz or perhaps even gigahertz, depending on the material. This can be very effective. So generally, metallic materials that are good at any frequency bandwidth, they need to be grounded, however, and of course, they need to be manufactured for the particular PCB in question. So those are some benefits and drawbacks. So it can work at any frequency bandwidth, but you need some customization and there's some cost with the manufacturing assembly on the PCB board. Ferrites are better suited for high frequency bandwidth, radiated noise. They come with self-adhesive, usually adhesive on the back, but one inconvenience is that you need to make sure it's conductive adhesive so that they are more effective, and they can be cut to any size. So sometimes people forget that, yeah, you can use copper tape, but why not use ferrite also in the EMI chamber to do some debugging? You can use this as well. It used to be that ferrites were quite expensive, so a lot of people didn't use them in production. But these days, the price of a metallic can versus ferrite shielding material, it's about the same. There is no difference between the pricing between the two. It's just more about the area that you're covering. So now you can use either material or both if you need to. So it's just a matter of more of understanding what kind of frequency bandwidth you're trying to suppress. All right, so let's talk now about our board and the testing that we did around this board. So here we have now it's a LED driver that we're going to use. It's an LED driver that uses analog silent switcher technology. A very effective method to reduce noise already. If you want to know more about the silent switcher, there is a lot of literature on it on our website, so you are welcome to take a look. In addition to that, this board has EMI filters. It has PWM dimming, and where you see the outline here, this blue outline that you see here, that's where we're going to put the shield itself to test this board. And where you see this exposed pad, that's where we connect the shield to the board. We connect it via clips. We're going to talk about that in a little bit as well. So here we have the setup that we did in the EMI chamber. You can see the LEDs, our load. Here's the board. And we have two types of shields. Why we're using two types of shields to test. One, as you can see, has holes. The other one doesn't. There has been a lot of questions as to whether holes play a role in having lower performance, reducing EMI compared to shields that are completely solid. So we want to show you what actually happens in both cases. And so without further ado, we move on to discussing that. So let's move here. Just some information about how we connect it, but let's look at the graphs. I think that will be more interesting for you guys to look at. Here we have our first slide. It's radiating emissions, and we have two graphs, and we have three scenarios. One is no shielding, which is in blue. Then we have in red our standard shielding with holes. In other words, some air ventilation. And then we have a green line solid with no holes. Again, we are testing to CISPR 25 class 5. And here you can see the two plots, and you can see what happens essentially when you have no shielding and when you have shielding. So from the plots, you can see on the low frequency bandwidth in both cases, you can see that having no shield creates a lot of noise, but as soon as you put some shielding material on it, we see some benefits. It's not very easy to see the red line. It's actually superimposed. It was so similar, the results, that they're actually superimposed on top of each other. So they look nearly the same. So you can see some of the red more here, just some variations that, again, if you test it on a different day, perhaps they would superimpose much better, but overall it's the same result for both, whether you have holes or no holes, compared to having no shielding at all. Here you can see that in the range, once we go above 10 megahertz, having no shielding material really starts to cause severe problems. You can see that as well in this region. So having no shielding material could be a problem. If you shield, of course, especially in the high frequency bandwidth, you can see some improvements. Here we're going to actually look at conducted emissions. So we have, again, two graphs, and you can see, again, what happens when you have no shielding material versus when you have either shielding material with holes or no holes. Again, the green seems to show more, but that's just because they're so well superimposed with one another that it's kind of hard to see the red, but it's there. And again, you can see where you get the most benefit is in the high frequency bandwidth above 10 megahertz. You can see how here having no shielding material is quite significant. You can see yourself failing in this particular frequency bandwidth. However, if you were to use either shielding with no holes or with holes, regardless, you get a significant drop in both scenarios. Here we have another set of results. This time we use a current probe conducted emissions, and again we conducted the same three tests: no shield, holes, and no holes. And you can see again some benefit. However, you can see how in this particular case, when we're talking about conducted emissions, since it's conducted, a shield will not have such a significant effect on conducted noise. After all, this is noise that's flowing through the board. So on the low frequency bandwidth, as you can see here, we are still failing. The shielding material of any kind would really not have any effect. So maybe here, what you want to do is still make use of a differential filter or a common mode choke, depending on the mode of your noise. And so you have to have something on the board. But once we go on to the high frequency bandwidth, we actually see some improvement. So what are we looking at? Well, yes, it's conducted noise, but as you know, this noise comes from, a lot of it comes from the MOSFET itself, from that voltage ringing. So it's noise that could be picked up by the board. Some components on the board could be picked up by the inductor and then fed back into the board again. So it's noise that came potentially from the MOSFET, went into air, was coupled into some devices on the board, and then fed back into the board. So if we put some shielding material, then that coupling, that air coupling that was happening can be reduced, and that can be most noticeable in the high frequency bandwidths. Anything above 10 megahertz, you can see some significant improvement. So even if we're talking about conducted noise, we can see that the shield can have some improvement in the high frequency bandwidth. So there's some benefits to having a shield even for the conducted EMI testing.
Thank you everybody for listening to this presentation. Thank you heavily for being with me today doing the presentation. And I'd like to add that Wurth Elektronik has a tradition of having local sales close to you. So please contact your local sales should you have any issue, should you have any question about this presentation or about EMI in general. We'll be happy to help, and we will be always there to help you designing the board. Thank you.